Hi, everybody. So my name is Kevin Wilson. I'm a principal data scientist at Newton, and we're an ed tech company down in the Union Square area. And I thought today I'd talk a bit about some of the problems that we face at Newton as an ed tech company, sort of talk about what we do, what problems we face, and then in sort of the latter half talk about basically some basic techniques for solving them. So hopefully, I'm not sure how familiar you are with like all of the sort of like usual modeling toolkit, things like maximum likelihood estimation and things like this. So hopefully I'm going to hit the right range of talks. And if anybody says this seems very boring, then feel free to be like, I know these things. But just to sort of give you an overview of what Newton does. So what we do is that basically there's a lot of online content available. There are huge hosts of this that's been put together by publishers over the years. The sort of print to digital education thing has been happening for a while. But a lot of times what isn't sort of taken care of in this sort of print to digital move is actually harnessing the power of like computers and recommendation systems and machine learning that we know about to sort of put data together about what students are doing and the content that they have. So what Newton does, we work with content providers to basically provide that piece in our platform. So we provide recommendations for students as they're going through courses. So they're working on things, they're doing really well. That probably means they should move forward. Oh, they're doing really poorly. Why are they doing poorly? Which of the things is it? Oh, it's like you should probably be working on this. So recommendations in that vein. Learning analytics for students and teachers. So what sort of data can we surface and aggregates thereof to students and teachers about what they're doing and what their students are doing to sort of make learning more effective for them. And also content insights for publishers. So what content is most effective? Are there pieces of content that some people really like, or the pieces of content that always cause people to do worse? I mean, these are, that's not an unheard of thing that happens in content. And so this is basically sort of what Newton does. And other things, but these are the main things. And so just sort of some overview of like what data problems we face. So we have sort of like, these are some example questions that we have to ask all the time. So big one is, what do students know? That's sort of the very first thing that we have to ask about any sort of thing we do. What do students know? And the second thing we have to ask is, when do they learn it? Because we're working with students learning things. And so there's this whole process of they start off knowing nothing perhaps, and they're supposed to go to knowing something. So anything that they know at day 1 isn't the same thing as what they know at day 7, isn't the same thing they know at the end of the semester. So there's sort of this temporal process that we have to deal with. Other questions that we ask are things like, are students engaged? That's very important. If they're very bored, they're not going to learn anything, et cetera. How effective are particular pieces of content? That goes back to that content analytics. And a big one, so if you ever talk to a data scientist and they don't mention that they actually ask the question, how do they measure success, then you should just stop listening to them. So I have to mention that we have to ask this question quite a lot of, how do we actually measure our own success? And so these are sort of some of the data problems that we face. And today I kind of want to talk about, talk about determining skill levels. And so these sort of problems fall into the what do students know and when do they know it? And in fact, the when do they know it's beyond this talk. I only have half an hour, and I can talk forever about temporal models of student proficiency and things like this. And so we're going to talk about the what do students know part of this. And specifically, there's sort of these big sort of 4 sub-questions of that. So how do you assess students, and what subject are you assessing them on, what time are you assessing them, and what setting are you assessing them in? And so the first question of how to assess, so there's this big problem where in a lot of things like, if you want to do something like, if you're an electrophysiologist and you want to say like measure what's happening in a monkey's brain, you shove electrodes in there and you figure out what's in a monkey's brain. Unfortunately, monkeys are not humans, humans aren't monkeys from this perspective. And so we can't shove electrodes in their brain. We can't see directly into their minds. We could only indirectly ask them questions about what they know. So actually setting up those questions of what we're assessing and how we're assessing is like a really, really important question. Alignment and coding are sort of the big buzzwords in that field of psychometrics. So this is one of the big questions we have to ask. What subject are we assessing is another big one. So this is part of the Common Core standards for 6th grade statistics and probability. That's the P at the bottom. And you can see there's sort of this whole hierarchy of subjects. Summarizing and describing distributions. Well, you can display numerical data in plots on a number line. That's one big bullet point sub there. Another one, summarize numerical data sets in their context. And that has even more sub bullet points. So you can imagine asking this question of what subject are we even assessing them on? And you can imagine, so like take the SAT. They wouldn't even be at this level. They would be at something much higher called math, right? When they're going to assess, their topic is going to be math. But from what we want to do, we want to sort of know about what people are at these sort of very fine levels. And there's a whole spectrum in between. And sort of making sure you know at what level you're at is another big problem that we hit. At a particular time, so this is a good like 1898 scene. When you ask people questions, both in terms of where they are developmentally as well as where they are in a course, are all very important. The particular time relative to their life and relative to the world can be very, very important. You can't reference things like the Eiffel Tower before the Eiffel Tower existed. And so like all these sorts of things really influence how you build questions and how you actually see their effect on students. And finally, in a particular setting, we all sort of know that high stress test environments tend to like cause people problems and whatnot. So that's that they do worse in high stress test environments, but they also do worse if they're on the beach, right? They're not going to be paying attention on the beach. So where they're doing these things can also influence what data you see and whatnot. And these are all sorts of things that we have to think about whenever you're sort of doing these assessment type things. And so today we're just going to take them all as fixed because once again, temporal models and latent and other sort of multi-factor models are beyond the scope of this talk. If you are curious about these things, then feel free to send me an email and I will talk your ear off for hours and hours and hours. But for this talk, just know that these things exist and we're going to be building into all of our models these assumptions that we've already started the assessments, they're well coded, we're assessing at a particular time in a particular place, and we know the subject we're assessing on. That's sort of big assumption that is broken almost all the time, but we're taking it as fixed for here. So thus is born the standardized test, and these are sort of the things that you're sort of used to seeing. This is kind of the epitome of what is, you're very controlled in all these things. It's a particular time, at the end of 11th grade. It's at a particular place, in a room in your high school. It's at, these things are very controlled, these questions. People spend years figuring out whether or not these questions are good. So thus is born the standardized test. And so this is sort of the far end of, like, when I say these things are fixed for this talk, I'm really talking about that's the only environment we have which approximates these things actually being fixed. Once again, at Newton, that's not the case. We're seeing people in their courses actually using these things, and so a lot of these things aren't fixed. So you have to deal with this noise. But just to keep a picture in your head for this talk, it's going to be talking about these sorts of environments. And these sorts of tests, so all these sort of controlled tests have a lot of sort of types of assessments you can imagine. I'm just going to keep simplifying here. So all these sort of have a good sort of notion of correct or incorrect, except for one of them, which is free response. And as we all know, free response questions are great for very broad overviews of what students know, but they make it very hard to grade in a consistent manner. And so, if you ever sort of sat through high school, your teacher probably handed you these rubrics that said, if you do, in the category of grammar, you can get a 3 if you do these things. And that's really an attempt to sort of build in a standardized grading for these types of assessments. That's very hard to get right. And so, hence we end up in the standardized assessment world. So today we're going to be talking mostly about, again, just to sort of set things, these sort of fill in the blank and multiple choice type questions where correct and incorrect is actually easy. So that's for today. Once again, there's a whole broad class of these things, but just to sort of talk about what models we're going to chat about today, sort of setting the tone. And so boiling it down to sort of what we're trying to do today is we're going to try to measure some sort of latent proficiency parameter, some sort of ability, some sort of skill that students have. And we're going to do it through binary tasks. So they get to answer a question and we get to declare them correct or incorrect. And so that's all we're going to get to do. And this is the very traditional setting of psychometrics. You're talking your ETS, your SAT, your ACT, all those sorts of things, like the very traditional setting. But sort of one thing that we will have some control over is that tasks are different, is that we can distinguish between tasks. Tasks can have properties. Some might be more difficult, some might be more discriminating. And so that's going to be one thing that we are going to have some control over. And moreover, there's a colon, a subtitle of this talk, which is like, or a sort of, there's whatever it is, other settings. And so this sort of notion of sort of measuring a latent parameter through binary tasks is not at all unique to education. And so just to sort of give you, where these sort of model classes come from, we've been talking so far about these standardized exams where your binary thing is right or wrong. But there's a lot of other things you can do. So you can talk about, if you ask a computer, is this the number 3? That's also sort of one of these classes where there's, a right or wrong answer. This is either a number 3 or it's not. And you can ask the computer yes or no. There are things like football games. There are, all these sort of head-to-head competitions that you can do where you have, you're trying to order teams. You're trying to rank them. And you're trying to say, well, I get a binary look into, I can't just sort of sit at them and say, like, your talent is thus, right? I only get to assess them through binary assessments, whether by playing other teams and whether or not they win or lose, right? And similarly, there are things like triplet questions inside of crowdsourcing where you can see things like, so this is like a far end of things, where you can say things like, which of these things on the right is more similar to the thing on the left? And out of curiosity, because this is a fun slide, who says B? Good, okay, I say B too, but so the rest of you I assume say C. It's the rainbow hair and the ears and the horn. It's just like, the C has a horn. It's like, obviously that's less similar. But anyway, so these are, so in this case, the sort of binary thing is greater or lesser. And so there's all these sort of ways where we can sort of start to ask about like the skills of various things, the skills of football teams, the skills of crowdsourcers, the skills of students, and always through these sort of binary questions. And so the rest of this talk, I'm going to give a quick tour of some of these objective functions that we might use in order to do this. And so hopefully this is kind of interesting for you all. And just to sort of set the scene once more, I like to think of a lot of these things in sort of terms of 3 categories. So, and it's mostly in terms of what questions you can ask. So these are my sort of 3 categories that I like to think of. So do your questions have deterministic or probabilistic responses? So what do I mean by that? If I ask a question between like the numbers 1 and 2, which one is bigger? That is a deterministic response, right? 2 is always going to be bigger. And unless like your computer gets bombarded by the wrong neutrino, it's always going to say 2 is greater. So whereas on the other hand, a probabilistic response might be something like it's raining outside when Michigan and Ohio State are playing, and so Michigan just happens to lose, right? That's a weird thing that should never happen, but the rain just sort of brought it on. And so those are sort of like probabilistic things. Like you don't necessarily know what the outcome's going to be ahead of time. In the student setting, this is something like imagine a multiple choice exam where if you have 5 responses to a question that are possible and you don't know anything, well, you have a 20% chance of getting it right just through guessing. That's very probabilistic. But there's a worse bit to that, which is that suppose you know enough that you can eliminate 2 of them. Well, now your chance is 33%. And so it's like the probabilistic is sort of multi-leveled here. So we're going to integrate all that out, it turns out, and so don't worry about it. But that's the notion between deterministic and probabilistic. There's also these comparisons between head-to-head and intermediaries. So head-to-heads are these things like comparing 1 and 2 directly to each other. Is this one greater than this one? It's things like baseball teams playing each other. You get to you're ranking baseball teams and you're throwing them against each other, and to ask which question, which is bigger? You're directly asking which is bigger. Whereas an intermediary might be something like you ask these sort of common questions between them. This is the exam setting where you say please answer these 10 questions, and depending upon how you answer them versus how Sam answers them versus how Julie answers them, we'll say which one of you is better at this topic, right? So that's sort of one of the, so that intermediary is sort of another sort of dimension. And a final dimension is whether you know the answer or you don't ahead of time. And so when I give somebody a multiple choice question, I presumably know that the answer is B. That's very useful to me because I can actually then assess whether or not the answer is correct. But there are things like those triplet questions where I don't actually know which one of B or C is more similar to A. Right? And I want to find out through crowdsourcing, say, which of these things is more similar. So that's actually a very hard case. We're not going to spend too much time on it. But as sort of a matrix, you can sort of think of these things in sort of this way. There are deterministic head-to-head and known answers are basically sorting. You have a list of a bunch of numbers and you want to sort them. We have great ways to do this. I assume you all know merge sort or something at least close enough to it. If you go via intermediaries, you get to things like 20 questions. I get to ask you questions, is it bigger than a bread box, and you answer them. But in this sort of left-hand category, it's more about, always in the deterministic thing, it's sort of about minimizing the number of questions I have to ask. Whereas in the right-hand category, it's much more about knowing how much confidence I have in any given answer before I could even ask how many questions I need to ask. So we're going to focus on sort of that top right-hand corner where the responses are known ahead of time, or the answers are known ahead of time, but the responses are probabilistic. And we're going to sort of divide these into ranking and proficiency. So, so let's start with the first one. So it is nearly time for the great game. And so this is a case of a head-to-head competition, non-deterministic with known responses. Known here is just that once the answer is given in this, once the answer is revealed, you know it's correct, right? There's no way the game is won or it's not. It's just what it is. So who wins in this case? So is there? Okay, is anybody not? Did nobody Michigan or Ohio State people got? Well, the answer is obvious. So in this case, it's a little hard to sort of go what we're going. But anyway, but if you take everybody, if you take all of 2013, if you take all of the FBS from 2013, and you sort of plot all these people. So here, winners are pointing at losers, and I've sort of clustered them by. You can sort of FBS. Oh, the football bowl. Oh God. There, thank you. Yeah, it's the Division 1 basically. They divided Division 1 between Division 1A and Division 1B basically, and they call them FBS and FCS. As of a few years ago, it's just football. Yeah, so these are the top college football teams in the country, and but you can see their conferences. So I sort of divided them by conferences. So the ones who are in the same conference are close together. They have little gray boxes around them. And you've got all these sort of like wonky arrows off to the side. These are those FCS teams, those sort of next tier down teams, which maybe only play one game against the big boys every year. And so that's what all those other arrows are. But you see in the sort of middle here, you see a bunch of these clusters, and you notice some like really horrible facts about this data set. One is that it's very dense in these conferences because that's how they work, but also it's very sparse as you sort of go between things. And so we can ask, so suppose that we have a graph like this. These are the questions that we've asked. We've had all these people play games. We can't have any more. The season's over, and they're going to get concussions if we have them play too much. So we can ask, so what sort of objective function might we want for this? So crowd participation, what sort of objective function would you want to sort of rank the teams if all you have is this graph? So anybody have a good idea? Sorry, what? Win-loss ratio, that's a good one. That's a good one. It's not the one I'm going to go for that second as opposed to first. So, what, sorry? Spielman correlation. I don't even know that one. Interesting. Okay, I don't know it.
It's between the true ranks and the ranks that
Ah, okay, I think that's basically what I'm going for. Okay, so we'll just sort it. So here I'll give you the objective function I'm going for, which is to minimize the number of out-of-order teams. So the idea is that, so suppose you had a situation like this, so Michigan obviously beats Ohio State, but then Ohio State beats Notre Dame, and then Notre Dame beats Michigan. So what we would expect in this sort of situation is that Michigan must be bigger than Ohio State must be better than Notre Dame, and Notre Dame must be better than Michigan, but we can't have that. So we have to put one person out of order. But the problem is that, like, who's number one, right? And the problem is that if you just know this, then I can choose any one of them to be number one, and my objective function is still equally minimized. So this is the problem, is there's sort of this big ambiguity here. There's no room to sort of bring in your domain knowledge that Michigan is obviously number one. And so so there's no room for priors. It's just completely ambiguous in a lot of these things. And it also has this other problem, which is that another name for this objective function is the minimum feedback arc set problem, and this turns out to be APX hard. So if you are not familiar with the class of APX problems, just be sad. It's basically NP hard, but for approximation as opposed to actually determining the answer. So this is very sad. But in case you want to use it, there are some approximations available to you in Python. So the igraph package has this lovely approximating algorithm called Eads algorithm. Never run the exact solution. I tried to get it for you all, but I let it run for 5 hours and it wasn't nearly done. So I gave up. But Eads algorithm is very good, and there are some extensions to it. For instance, my coworkers, Ruben Naif and Zach Nichols, had this paper coming out in its workshop in 2014 in a few weeks about improving it in the context of education. There are some objective functions. There's sort of some maximal goodness properties that you can get out of it. But so now we're going to go back to the win-loss ratio. So I'm going to do a fancy version of the win-loss ratio, and this is going to be the sort of first track into sort of what we do at Newton frequently. So the idea is sort of define this latent awesomeness parameter, which we'll call theta t, 1 theta per team. And this is going to determine the probability of winning in a head-to-head matchup. That's what it's going to be. And now we have a problem where we can just maximize the likelihood, because we can determine this probability, and we can just go maximize the function. So in general, principle is that these combinatorial problems, like number of edges I removed, is a hard thing. If you can turn it into, I've got a real number, and I want to maximize some function, it's a lot easier. It's still frequently hard, but it's like a lot easier. So here, what we're going to do is this awesomeness parameter is going to be the thing we're going to rank on. It's going to be some random real number that we don't have too much control over. But the point is that we've sort of set it up so this is the parameter that controls your probability of winning a head-to-head matchup. That's this notion of awesomeness that we want. And it's a real number, so we can maximize the function. This becomes much easier for computers to deal with. So the traditional way of doing this is something called Elo's method. And this is sort of developed in the 60s for chess ranking. And the idea is that, so you see, we just define the probability that A beats B. Team A beats Team B as the logistic function of the difference in their skills. So these theta A and theta B are their skills and logistic of their difference. So if you're not familiar with the logistic, it's this sigmoidal curve. And it shows up in logistic regression, which I assume all of you know. And if you think of it this way, this is basically logistic regression where the points, the things that we're trying to classify are the games, and the features are the skills. But the point is that we care more about the skills, we care more about the features than we do about the points, which is the opposite of logistic regression. When you think about logistic regression, you really want to classify points. You don't care about the features per se. Here, you really care about the features. The points are already fixed for you. So that's kind of what we're doing with this. This is the idea. And just to note, if theta A is huge, then you get 1 over 1 plus 0. And so that's going to be, the probability is going to be 1. If theta A is very small, you get 1 over 1 plus infinity, which is 0. So the probability of winning is very small. Backwards.
Would you like a pseudocount, let's say, to correct for that?
You can. Yeah, you can definitely do a pseudocount kind of thing to correct for that. But we're assuming they only play each other once. And so there's sort of, like, this is the pseudocount in some sense, is the probability is kind of the pseudocount. And so in the traditional way, we take the argmax over theta, we sum over the log likelihoods. And if you do that, so I think I'm not going to have too much time. Let's see, what's here? Oh, I don't have a time. What time is it? How much time do I have left? Oh, great. OK. So I'm probably not going to have time to show you too much code. But I do have a bunch. I have all the sort of code that generates this online. And there are exercises for you, in fact. And you may feel free to submit pull requests which solve the exercises. And I will. I promise that I will get with them within a week, unless somehow this video goes viral and I get, like, 1,000 of them. But there are exercises with the Python sort of how I did all this online, including IPython notebooks and whatnot else. So if you do this, you actually end up with this list. If you do this for those football games, you end up with this list. And so who can tell me sort of the weird thing about this? Like the really, there are at least 2 weird things about this. Sure.
There is sort of notable jumps between the scores. Like the bottom
Yeah.
numbers are about the same, but the top you have like 34, 29.
Yep. So that's very true. So you've got this very sort of big jumpiness in the scores. That's actually if you actually look at the distribution, they'll probably look about normal. And that's actually a good thing I didn't actually do, but you should look at them. Other things you can notice?
Yeah, the top teams are FCS teams that are probably really high due to small sample sizes.
Yeah, exactly. So yeah, here's your domain knowledge here. So what the heck are these people doing up top? Also, Michigan's not on the list. That's really the third thing that you should notice, but Ohio State is. Sorry, it's next week. I have to really be going for this. So but you notice, so Georgia Southern, North Dakota State, Northern Iowa, McNeese State, Towson, Fordham, they're FCS teams. Like, what are they doing there? Like, they obviously are not as good as Alabama, Auburn, Missouri, Louisiana State, LSU, all these people. I mean, obviously, if you have the domain knowledge. Right? And this is the key, that domain knowledge here. Remember, that graph is very, very, very sparse. And so when that happens with these low sample sizes and that sparsity, you end up with a lot of things like this. And so what can you do about it? Well, so there are these extensions that you can make to this very easily. The traditional thing to do is to add priors, so in these regularization terms. So for instance, you might have a prior that says, Florida should have a very high starting score. And Towson, on the other hand, should have a very low starting score. This is like a very thing you might want to do. And obviously, bullet point number 3, And so it turns out there's sort of some fun things that this does for you, one of which is that it makes your objective function convex. So for those playing along at home, this is not a convex function. And this is if that means words to you, but it's only convex because of one-dimensional thing, which is that you can add a constant to all the thetas simultaneously, and you get exactly the same number. So if you theta A plus C minus theta B plus C is theta A minus theta B. So it's not convex because it doesn't have a unique maximum. So it's not convex, but it turns out you're adding these priors will make it convex. So for those of you who know these words, that's a good thing. And moreover, it allows for you to toss in this domain knowledge to make it for sparsity. And that's really one of these key things, is that when you have these sparse samples, you really have to include that domain knowledge. And sort of one of your challenge exercises, if you go home and do this, is to make Boise State be number 1. Because one of the great criticisms of the Bowl Championship Series was that Boise State kept going undefeated for years and years and years and still ended up in 12th place every year. And it's because the Bowl Championship Series was putting these massive priors on it, basically. Say, like, Boise State surely can't be greater than 12th place because they're Boise State, right? And so these are these sort of things where that was them imposing prior knowledge on this ranking, and then saying, like, okay, well, this is the order we're going to get. So one of your challenges basically is that if you put on different priors, you can sort of force various different rankings on this. And this is one of your great challenges as a data scientist, is being judicious in how you do that and knowing the consequences of it. So go forth and explore with priors in this case. There's also one other sort of extension that you can do, and just because I mentioned Elo, this is actually what he did. The stochastic version of this model, the stochastic gradient descent version of this model, it has a very nice update function. So if you know SGA, it's a very, very simple update function, and this allows for all those people who don't want to recompute the maximum every night. So somebody like Xbox, who has millions of users, but doesn't want to actually have to go forth and do a big Hadoop job every night to update the rankings because they don't want to spend the money on it. They can just do this online, and it's close enough. So this is the other great thing about this particular thing for this problem. And in fact, it's used by, I think it's still used by Xbox Live. It's called TrueSkill for them. And Yahoo Games, I think, has something similar, and there's a bunch of other people. Okay, but warning, just to go over again. Note, the sparsity means that priors have a strong effect. The top of the heap has little incentive to play, so this is this small sample size problem, basically. And really, one of the big things is that there's no room for improvement. You're not tracking people over time, and that's sort of a big problem. Just to quickly go over the case that Newton cares about, and I have 3 minutes, I think. So in this case, so what happens if you have an intermediary instead? And this is the exam context. And so this is the case of proficiency. And here the objective function, we defined it the same way, except that questions are now essentially different students. So we just sort of say that we put a head-to-head contest between students and questions and students. And it turns out if you do that, you get the exact same objective function, just slightly modified a bit. And you end up with the probability that student gets question Q right as being this difference here. Theta is going to be a student's proficiency, and beta is going to be a question's difficulty. And you can take an argmax, just like we did before. Now it's over thetas and betas. So it's over the probability. This is the probability that they get it right. So you take the sum over the questions they got right minus the sum over the questions they got wrong. And that's your thing. And just to point out one more time, so that in case you haven't seen this before, that kink where 50% is what beta is going to be. And so if you make the question really difficult, it moves to the right. And the probability of a student with a fixed proficiency getting that right goes to 0. Whereas if you move it far to the left, so beta in the bottom is -2, it all of a sudden goes up to 100%. So you can do the same sort of thing. Once again, code's online. IPython notebooks are online. Bunches of district plays and whatnot else. Unfortunately, this was meant to be a 40-minute talk, and it's apparently only 30 minutes. So so there are features of this particular thing. So students and questions are ranked on the same scale. Items can be more or less difficult, and you can tailor an exam to a particular grade level. These are like a bunch of things that this sort of gives you, where if you can rank students, if you can rank questions simultaneously, you can start to target particular difficulty levels of students and whatnot. But it still has some problems. Sort of the big ones are things like distinguishing between features of questions. Maybe that big question, getting that assessment right, coding it right. Which concept is it assessing is still a very hard problem. And so you can imagine it might assess multiple concepts. What does that mean? Turns out a simple thing to do is to just like logistic regression, add features. Just right or wrong, this is obviously not a real use case for a lot of people. You have free responses that may be kind of right. And also learning over time, still a problem, but temporal models of this are like a longer, much longer discussion. Email me if you're really curious about temporal models of student proficiency, because those things are picky. And that's basically it. So I have some pictures of performance, and I guess I can show you one picture because I promised some pictures in the abstract. So you can see, so we sort of randomly simulate some data, and you can see that this does in fact recover the original. It is a good recovery algorithm at the very least from simulated data. So I promised you some pictures. Here are some pictures. Use the Seaborn library, by the way. These things are awesome. And yeah, so high Pearson R's in both cases. OK, I'm out of time, so I'll skip all the other things and just say thank you. The code is here. Feel free to go forth. It's PyData 2014 at my GitHub. It's KH Wilson. So and do the exercises.